2, 3 and 5 and pi are irrational numbers. In general, square root x is irrational where x is a prime number. We can have a simple definition of irrational numbers. A number is called irrational if it cannot be written in the form of p upon q, where p and q are integers and q is not equal to 0. We need to understand the following theorem in order to prove a given number irrational. According to this theorem, for a prime number p, if p divides a square, then p also divides a, where a is a positive integer. Let us now prove it. Let the prime factorization of a be as follows. A is equal to P1 into P2 into P3 and so on till Pn, where P1, P2, P3 till Pn are prime numbers and are not necessarily distinct. Therefore, on squaring both sides, a square is equal to P1 into P2 into P3 till Pn into P1 into P2 into P3 till Pn, which is equal to P1 square into P2 square into P3 square up to Pn square. Now, we are given that p divides a square in the theorem. Therefore, from the fundamental theorem of arithmetic, it follows that p is one of the prime factors of a square. However, using the uniqueness part of the fundamental theorem of arithmetic, we know that only prime factors of a square are p1, p2, p3 up to pn. So p must be one of p1, p2, p3 up to pn. Now, since a is equal to p1 into p2 into p3 till pn, therefore p also divides a. Using the above theorem, we are now ready to prove that square root of 2 is irrational. Let us base our proof on the method called proof by contradiction. To prove square root of 2 as irrational, let us assume to the contrary that square root 2 is rational. So we can find integers r and s where s is not equal to 0 such that root 2 is equal to r upon s. Suppose r and s have a common factor other than 1. Then we divide r and s both by the common factor to get root 2 equal to a upon b, where a and b are co-prime. Remember, co-primes are those numbers which do not have any common factor other than 1. So, on cross multiplication, we get b root 2 is equal to a. On squaring both sides and rearranging, we get 2b square is equal to a square, call it 1. This implies, taking 2 to the other side, we get b square is equal to a square divided by 2. Therefore, we can say that 2 divides a square. Now, from the already proved theorem, it follows that 2 also divides a. Thus, we can write a is equal to 2c for some integer c. Then, on substituting a is equal to 2c in 1, we get 2b square is equal to 4c square. Divide both sides by 2. This implies that b square is equal to 2c square. So this means 2 divides b square, and from the earlier proved theorem, 2 also divides b. Therefore, a and b have at least 2 common factors, that is, factors 1 and 2. But This contradicts the fact that A and B have no common factors other than 1, as they are supposed as co-primes. This contradiction has arisen because of our incorrect assumption that square root 2 is rational. We therefore conclude that square root 2 is